The next couple of weeks we're going to be focusing on the atmosphere, and since the atmosphere is an envelope of air that surrounds the Earth's surface, we need to talk a little bit about gases and also about energy. So let's start by talking about the composition. That's a little wide. Let's go back to this one. Of the atmosphere. So most people are aware that the majority is nitrogen gas, and it is 78.09% nitrogen. It is 20.95% oxygen, our next largest component, and then a very small minority of gases after that. So argon is almost 1% of the atmosphere. And then the next two most abundant gases are carbon dioxide and water. And water I'm listing last because its composition varies so much. So carbon dioxide is about 0.04%, and water can vary between about 1 and 4% depending on a lot of factors. Like obviously you're probably familiar with some days where it's really humid. Those are days where you have more water that's dissolved in the air. And then other days that are super dry, or other places that are super dry, are going to have almost no water dissolved in the air. I don't think it technically goes all the way to 0%, but that's okay. We will worry about exact percentages later on. So with carbon dioxide, most people are pretty aware that carbon dioxide is of concern to us because it's a greenhouse gas, and we'll talk more about what that means a little bit later on. But for right now, it's an interesting thing for us to be aware that the Mauna Loa Observatory over in Hawaii has been tracking carbon dioxide data for probably 70 years anyway right now. And so if you are interested in checking out more about greenhouse gases and carbon dioxide in particular, you can just do a quick search on the Mauna Loa Observatory. I'll probably link it to the Moodle as well. And you can check out a lot of information and data that they're gathering on greenhouse gases, not just carbon dioxide, but others. So I checked yesterday, and they said that the current estimate on carbon dioxide is 412.88 parts per million. And since we had a little background information topic on parts per million and how it relates to concentrations, let's take a quick moment here and verify that 0.04% is the same as 412.88 parts per million. If you need to, go ahead and pause the video, go back over to the other parts per million video, review that, and then come back here and confirm this calculation. So I'm going to set it up, and then I'd like you to pause the video and do the calculation, and then turn it back on, and we can check it together. Okay, hopefully you had a chance to go and do that calculation. So we all know that if we're talking about percent, this symbol means that we have 0.04 parts in 100 parts. That's what a percent means. So if I work that out mathematically, that means I have 0.0004, or 4 times 10 to the minus 4 is the fraction that is present there. So in parts per million, we know that we have 412.88 parts per 1 million parts. So we set up the math exactly the same way. If we work this through, we will get 4.1288 times 10 to the minus 4. And so if we are just paying attention to 1 sig fig, which is what we had up above, then these are the same numbers. So yay, that works out. So carbon dioxide and water seem to have pretty small concentrations in the atmosphere. Even argon is not terribly abundant. But when we think about these gases, 1% of gases, there are so many gas molecules out there that you can have some pretty small concentrations and still have noticeable amounts of that gas. And so we have lots of trace gases in addition that we haven't even mentioned, right? So many. I mean, everything that you smell is a gaseous component that is now entering your body, right? Sometimes that freaks me out, but a lot of the time I just think, whatever, my body can handle it. So we have some things that are air pollutants, And usually the air pollutants are the trace components that are problematic to us. Things like carbon monoxide and nitric oxide, or any of the nitrogen oxides, ozone, volatile organic compounds, VOCs. There's all kinds of different air pollutants that are out here. And then I'm just going to say, odors, and I'll just say benign ones. So the nice smell of the rose is a gaseous component, doesn't travel very far. Vanilla, that's a gaseous component. So we have lots of volatile organic compounds that are not considered air pollutants because they tend to be benign and not problematic to us. So anyway, that's enough about trace gases for right now. And so if we think about gases and the atmosphere, one of the things that we need to remember is that gases circulate in the atmosphere. And so if we are concerned about air quality and about the environment, then the first thing is we need to know what kinds of gases are in the environment. We need to know what those gases do, like what kind of chemical reactions they participate in. And if those chemical reactions are problematic, or even if they aren't, how long are they staying in the atmosphere? So that means we need to learn a little bit more about the atmosphere. And you may or may not have ever studied the atmosphere. I don't think I've ever had any classes that really talked about it. So I'm going to kind of go ahead and talk about the regions of the atmosphere here for a minute. And so I'm actually going to switch over to another visual that is a little bit easier to look at rather than just my writing here. So in this visual, we can see that we have several layers. And the layer that we all exist in, and that contains 75% of all the gas in our atmosphere, is the troposphere. You've probably heard this name before. The troposphere contains every physical structure on the Earth. All the mountains are in it. Most of the weather is in the troposphere. And then at the end of the troposphere goes about from sea level up to about 12 kilometers above the Earth. And then there is a 6 kilometer or so region called the tropopause, where it transitions from the troposphere into the stratosphere. And of course, you have to remember that there are no hard boundaries in the atmosphere. I mean, it's just a region of gases. And so scientists have kind of classified different regions based on how gases behave there and what's happening in them, but there is not like a hard line. If you send a rocket up, there's not a little, you're leaving the troposphere now, so just keep that in mind. These aren't hard boundaries. So the stratosphere is our next level up, and it contains most of the rest of the gases, about 24% of the gases. It goes from about 18 kilometers above the Earth to about 50 kilometers. You probably know that the ozone layer is located in the stratosphere. It's at about 25 kilometers up, and it goes over a band in the stratosphere. We'll talk more about it later in detail. And so just like the troposphere ending with the tropopause, the stratosphere ends with a stratopause at about 50 to 55 kilometers in elevation, and then it transitions into the mesosphere. And the mesosphere continues from about 55 to 80 kilometers, ending in the mesopause from about 80 to 90 kilometers. And past that is the thermosphere, up until about 600 kilometers above the Earth, where it kind of fades away into nothing, called the exosphere. Almost all of the weather that happens on the Earth is in the troposphere. We're going to learn more later about polar stratospheric clouds, which you can imagine are in the stratosphere. And they're in the lowest level of the stratosphere, and they can overlap with the ozone layer. And what else we know about the stratosphere is that if we were sending up any weather balloons, they would reach the mid-stratosphere. Now, the other things that might be familiar with the atmosphere, if you've ever watched a meteor shower, those meteors are burning out in the mesosphere. Because in the mesosphere, even though we don't have a lot of gases, we have enough that's where those particles are going to start, those little tiny rocks are going to start burning up because there's enough gas there. And then up in the thermosphere, you might have seen the aurora borealis once, and if not, maybe you've at least seen videos of it. anyhow, it happens in the thermosphere and maybe the very top of the mesosphere, so pretty high up above the Earth. So we're going to switch back over now. I'm going to write down these names of the regions just kind of to have a summary of them. So we have the troposphere, and we have the stratosphere, mesosphere, thermosphere, and the exosphere. So I said that almost all of the gases are here in the troposphere, and then the next most abundant region is the stratosphere. And of course, the reason for this is gravity, right? We all know the Earth has gravity. Well, everything experiences gravity. It's a force of masses attracting each other. But the Earth is the biggest, heaviest thing nearby, and so all of the air is being attracted down toward the surface of the Earth. So most of it is going to be down here near the troposphere. And so that makes pretty good sense. All right, so if we want to talk about pressure of the atmosphere, of course, most of the time when we talk about the atmospheric pressure, we're talking about it at sea level, where it's approximately 1 atmosphere or 1 bar or 760 millimeters of mercury, depending on what kind of units you like to use. But we can actually calculate the pressure at any atmosphere or at any elevation. I guess it's called altitude when you go up above, right? The pressure at any altitude is the sea level pressure, about 1 atmosphere, multiplied by a decreasing exponential function. So this is e to the minus z over 7.4. I'm presuming that this 7.4 is probably some constants that all kind of got approximated in here. So this is just the approximate pressure, because pressure does vary quite dynamically. So z is the altitude in kilometers, and then this is the atmospheric pressure. And you can calculate this using any units. So it doesn't matter if you use pressure in atmospheres, in bar, in millimeters of mercury, in inches of mercury, in torr, whatever your favorite pressure is, pounds per square inch. All right. So we've got this as a way to calculate the approximate pressure at any elevation. So that's kind of useful. All right. So this kind of gives us some basics about the regions of the atmosphere and how much gas happens to be at any one place. But the other thing that we were talking about was, how do gases in the atmosphere circulate? And possibly even why, right? So I'm going to switch over again to another visual. So this diagram gives us several pieces of information here. We can see here is our equator, and at our equator we have these cells, these roll cells of air that are rising near the equator and then driving themselves north or south, depending on which roll cell they're in. These guys are the Hadley cells near the equator. At the mid-latitudes, this is called the Ferrel cells, and they do the same thing. And then up at the poles, we have the polar cells. At the same time, we also have wind patterns that are happening. So we've got westerlies sort of in the mid-latitudes that are heading, you got it, west. Same thing is happening up north here. We've got westerly winds. And then in the Hadley cells, we have mostly winds heading east. And these are called the trade winds. So I'm going to switch over to another diagram. This trade wind diagram takes out the roll cells, so we can kind of focus on what those winds are doing. So you can kind of get a sense for how our westerlies are going mostly west along the mid-latitudes. That's mainly what we have over here. across most of the United States. And then we have some trade winds heading northeast, and these other ones heading southeast. And then we have these places where the winds hit each other. So you can kind of see they've got this diagram in the Atlantic and near the Caribbean here, where we're forming hurricanes where those winds meet and mix with each other. And the same thing happens down here by Africa and Southeast Asia and Australia, that you can get this swirling effect from where those winds are meeting each other. So let's head back to our roll cells. Okay, so here we are at one of the NOAA websites that's talking about weather. I'm also going to link it from the Moodle. And this gives us a better diagram of what's happening in some of those cells. So this one is focusing on the Hadley cells, but really the same kind of deal is happening with all of the cells. It's perhaps amplified here in terms of warm, moist air because we have warmer temperatures here at the equator and plenty of water available, but this is happening for all the cells. So what's going on right here with those cells is that we have this warm, moist air that is rising and forming clouds. Those clouds are then being carried, the water gets condensed and falls again, the air cools and falls again, and you get this cycling effect. So this heating and cooling, remember that the cycling of the air in these different kinds of cells means that, well, this is north-south cycling for one thing, regardless, right? If we're heading toward the northern part of the hemisphere, then we're heading toward the north. If we're going south, it's going south. So this is north-south cycling, and gases that start in a Hadley cell mostly stay in a Hadley cell. And this is true also for the Ferrel cells and the polar cells. So this north-south cycling does not tend to mix gases from the northern hemisphere very quickly with gases from the southern hemisphere. More on that in a little bit. But at the same time, because of those westerlies and trade winds, we actually have east-west cycling pretty quickly. So on one hand, I'm going to switch back to OneNote now with our north-south cycling. So air is in the cells. It can take 4 to 5 years for northern hemisphere gases to reach the southern hemisphere. And this is usually the direction that we're paying attention to it because the majority of the population centers are in the northern hemisphere, and so the northern hemisphere is making more air pollution compared to the southern hemisphere. And so because of that, we are mostly tracking the air pollution from the north heading into the southern hemisphere. So this is on the multiple year scale for gases to mix out of the north-south. But for east-west, this is quite quick. This is more like, 5 to 10 days, for gases to go around the world. So maybe you remember, I think it was last summer, we had a big windstorm in China that raised a lot of dust. And so the dust blew across the Pacific Ocean, and it didn't impact up here very much. It mostly ended up arriving in California, but they had a significant amount of dust in the atmosphere because there was these dust storms over in China. And it only took about a week for these to pass. So we talked about how gas is circulating. We have these two different foci, right? We've got the north-south circulation happening in cells, and we have the east-west circulation that's happening along these sort of more continuous flow routes. And the Y has to do with two factors, right? One of them is that the Earth is rotating. And so as the Earth rotates, the gases sort of get pulled along, right? We have kind of like friction with the ground, and so that pulls them along and they get swirled around the Earth. But we also have the the hot-cold energy cycle that's happening in the Hadley cells, right? This east-west rotation is mostly related to the Earth rotating, but these cells have to do with an energy cycle. And this energy cycle means that we're going to have to talk a little bit about thermodynamics for a little bit and gas energy. So let's think about it. All right, that diagram that we had talked about how we have warm, wet air that is rising. And this was from the equator, right? I'm not sure what that was supposed to be. I guess a center point, right? So we have warm, wet air. That means that we have a surface or an area that has a lot of liquid water. And this liquid water is getting converted into gaseous water. And then as we rise up, this gaseous water, it condenses into clouds, and it flows either north or south, depending on which part of the Hadley or which Hadley cell it's part of. This liquid in clouds goes for a while, and then maybe it falls down as rain. And at the same time, we have gas cooling. And so the gases are also falling too. So the gases are rising here. And then it cycles around again. So we have this heating and cooling cycle. And these particles moving. So if we think about the gas particles, right? We talk about hot air rising. So we can model gases pretty well using the ideal gas law. And if you need a reminder about that, I have one at the top of the Moodle. You can kind of pause and go and remind yourself about that. So if the temperature is increasing, then the pressure of the gas particles is going to be increasing as well. And this may not seem totally like, how do I think about that, right? How does gas pressure work on an atmospheric scale where it's all sort of connected together, right? So it might be easier instead to think about kinetic energy, although I'm going to come back to the gas pressure idea here in just a minute. So the kinetic energy of anything is 1/2 mv squared. And if we think about gas particles moving at speeds, then we can actually come up with some averaging with statistics. You do not need to worry about why. But you can study this in physical chemistry if you ever take that class. If you're a chemistry major, you will. And so with statistics, we can find out that the kinetic energy of gas particles will be pretty well modeled by this 3/2 RT. So R is the gas constant again, and then T is the temperature here in Kelvin degrees. And so either way, we can see that as the temperature increases, the kinetic energy increases as well. So let's get back to this idea of pressure or potentially kinetic energy, and let's think about sort of a column of gas above the surface of the Earth. And this column of gas has some pressure, right? And it's atmospheric pressure initially. I'm going to just make some P naughts on the other sides too, right? But I'm going to focus on this part of our gases because I'm going to imagine that this is my part where the temperature increases and so the pressure increases. And so rather than just being at P naught, I'm going to clean this up a little. I now have some new pressure, P prime, where P prime is a little bit higher than P naught. It's not like it's a ton higher or anything. But let's think about what else is happening down here. This P naught, this is our maximum pressure normally, right? That if we go up, pressure is less because we know there's fewer gases because gravity. is attracting all of those gas particles down toward the Earth, right? So that means that these little gas particles in this place where the temperature has increased, they're moving faster than their buddies nearby. And so where are they going to go? They're going to bounce all around everywhere, but it's going to be easier overall to have some of them go up because there is fewer gas particles up here. And so those hot particles are going to find it a little bit easier to head upward because they're not going to have so many particles to bounce against. So our net direction of movement is going to be increasing, which is why we say that hot air rises, because it does. And so this is what generates those rolling cells, right? As our hot air rises, as it gets higher and higher, then we have particles condensing out into clouds. And let's get into that in just a second, okay? So I want to talk about the energy that's involved in the water that's in the air, all right? Because water, we said, water vapor is one of our most dynamic gases. And water is very interesting because it is also a greenhouse gas. And again, we'll get back to that more later. But because it has a really dynamic water cycle where water particles, like each individual molecule, they only stay in the air for a few days. So gaseous water cycles through between gas and liquid very quickly. And so overall, the amount of water vapor that is present in the atmosphere is pretty constant. And so, so we don't actually worry about it that much as a greenhouse gas because the amount of water vapor does not change in any, really reliable way. So let's talk about energy for a second. Because one of the things that I was talking about here was this transition between gaseous water being evaporated and then condensing out, right? That we have evaporation as the hot water molecules get carried up into the air, and then we have condensation as the particles turn into clouds. So let's talk a little bit about energy because this is a phase transition. So the energy that I want to talk about here is the enthalpy that is involved in this physical process. So I'm going to post another video about enthalpy and thermodynamics in case you need that review. But just to give you that quick reminder here, enthalpy is energy, and it's heat energy that's involved in chemical or physical processes. Chemical and physical processes. So any chemical reaction, any physical process, they all involve some heat flow. All right. So when we think about going on some kind of a phase transition, so from solid to a liquid or liquid to a gas, if I'm going from a solid to a liquid, energy has to go in. Solid is a condensed phase. The particles are bonded together. And if I want to go to a less condensed phase, I have to flow energy in. And so I'm going to say that this delta H is positive. And I would call this endothermic. That might be familiar to you. So this energy is flowing in to break up some of these bonds that are holding the solid into its solid shape and let it start to flow as a liquid. And the same thing is true if I go from a liquid, which is a condensed phase, into a gaseous form, which is not. Those particles are all kind of separate and independent. Again, the energy is going to flow in. But the thing about phase transitions is that this is reversible. So anything that I can go forward, I can also go backward. So if I go from a liquid to a gas, now the energy is going to flow out. And so I'm going to call that delta H is negative. And delta H less than 0 is called an exothermic reaction, which also might be familiar. I didn't really leave myself enough space, but the same thing is true here. If I go from a liquid to a solid, energy is going to flow out of that system. So let's get back to thinking about water. And so if we look at water, we have this natural cycle of water, gaseous water, we have liquid water that is being evaporated. And how is it being evaporated? Well, if we think about what the weather is doing, right? We have some sunlight coming in, and the sunlight is evaporating the water. So this is where the energy in comes from. It's coming from our sunlight. And then we have these gaseous particles rising up into the air and then condensing out into the liquid. And as they condense out into the liquid, then I have energy being released out into the environment up in, I guess, the upper troposphere, right? Where the clouds are. So I've got this flow of energy too. And this flow of energy is part of what fuels those Hadley cells. It's not just, the wind. It's also this energy cycling that happens. So when we look at this energy, the enthalpy of vaporization for water, and I'm going to explain this bubble in the thermodynamics video. If you look this up, we can see them in tables. It's 40.65 kilojoules per mole. This is a really common unit that we will see for energy, that we have kilojoules, which is an energy unit, and then we have a quantity of stuff, the per mole. So it takes energy to change the phase, and you can find this kind of information in tables all over the place. It also takes energy to increase and decrease the amount of the temperature of materials, right? Because we had liquid water here, we had gaseous water, we had to evaporate it, that's a phase change. But then we also had warm air, and so as we are warming up those gaseous water molecules, that took energy too. So the energies that are involved in changing temperature are heat capacities. You might also have heard of specific heat. These are the same thing. So heat capacity is the energy that is required to raise the temperature of a material. And we can find this information in tables. I'm going to switch just really briefly over to a table for us to take a quick look at. This is a scan table from a textbook, and as you can see, there are lots and lots of thermodynamic properties. These are just a few substances here. Notice here at the top that these thermodynamic properties are listed at a specific temperature, and I promised I would explain this bubble here. The bubble is because it's at the standard state, which is 1 bar, and then there's more to the bubble that I'll explain in the thermodynamics video. So this table has enthalpies of formation, which we'll talk more about in that thermodynamics video. You don't really need to worry about Gibbs energy, this delta G, or the entropy right now, but the heat capacity values, that's this Cp. And so if we go down and look at water, we have 75.291 for liquid water and 33.577 for gaseous water. And so it takes a little more energy to increase the temperature of liquid water than it does gaseous. And this makes pretty good sense if you think about how water that's a liquid is a condensed phase, and so you have to contend with all of those intermolecular forces, and that makes it a little bit more challenging to make those particles vibrate more quickly. Okay, so our bottom line from all of this is that I just want for right now this brief summary of some big ideas regarding energy, which is that it takes a lot of energy, quite a bit, to convert a liquid to a gas. Then it takes less energy, but still some, to raise the temperature of a liquid. And it takes even less to raise the temperature of a gas. So when the sun irradiates the Earth, some of the energy is going to be used to warm water, melt ice, some of it's going to be absorbed by the soil. We can get a pretty good sense for what these energies look like. I'm going to switch over to an energy balance diagram here real quick. So don't worry too much about the numbers here. I just want you to kind of look at the big ideas. So the big ideas here are that we have some sunlight coming in. Sorry about that. Let's try that again. All right. So we've got some sunlight over here, and some of it's absorbed by the atmosphere or by clouds. Some of it reaches the Earth, and then we use it for things like growing plants and making vitamin D. Some of it's reflected, some little amount. Some of it's reflected by clouds. And then the atmosphere, because it's absorbing some of this energy, it's also emitting mostly infrared energies. And so it can emit in both directions, out toward space and down here toward the Earth. And then our Earth is actually warm, and it's giving off some heat too. So we've got some emitted by the Earth that is absorbed by the atmosphere, and some just goes directly into space. So we've got a lot of energy going on, and this is just intended to be an initial introduction of thinking about energy and how it balances in our atmosphere and in the land. All right. So there is this pretty complex interplay between energy coming in, energy coming out. And I think that we're going to go ahead and do some practice calculations. I have posted assignment number 7 onto the Moodle. I'm writing the problems this time, so they're not book problems. And so go ahead and give those a try. And then I'm going to be posting some more information about specific parts of the atmosphere as well.